All right, in this question, this is the same as the previous part, but the only difference is that in this case we're looking at the t-test to find the critical values. And if you remember, I will just show you, this is the situation where you have sigma unknown, so you have the sample standard deviation S, you'll see it here in the formula, okay, and the population is normally distributed. Okay, so let's go and compute it. It's exactly the same as the z-test, but the only difference is that here you will be using the t-table, not the z-table. So let's see. I start with the first one. Determine the critical value for a right-tailed t-test with alpha equal 0.01 and n equal 12. So because you know that it's a t-test, immediately the best thing to do is compute the degrees of freedom. This is, you compute it from n. If the sample size is 12, then the degrees of freedom df is always n minus 1, which is in this case 12 minus 1, it will be 11. So this is an important number for you for this question. And the other one is that alpha is 0.01. And also the fact that you have a right-tailed test. A right-tailed test is one-tailed test. So now when we go to the t-table, you will see that it is a right-tailed test. Right-tailed means that it's one tail. So you look at this part of the table and you go to the alpha that's given. So the alpha that's given to us was 0.01. And the degrees of freedom turned out to be 11 in this case, because n was 12 and 12 minus 1 is 11. And all what you have to do now is go from 11 to this number and go down to this number, and this would be your t critical value. So in this case, the critical value is 2.718. This is all what you have to do with the t-table. The t-table is much easier to apply than the z-table. But there is one thing that you need to know about the t-table that when we do the left tail test, you will see. So let's go back and put this 2.718. So we found that the critical value, this t, it's a t of course, the critical value in this case is 2.718. And so again, this is the same thing as the z value. If you, the z test, this region here will be the rejection region. You reject the null hypothesis, and the non-rejection region will be this one here. So if you compute your t, you remember that t in this case it will be x bar minus mu over s, because the sigma is unknown, over radical n. So you compute this, and whatever you get, whatever number that you get from here, you see where it is. If it falls in this area, then you reject the null hypothesis. But if it falls in the non-rejection region, then you do not reject the null hypothesis. So let us write all of what we found. We found that the critical value is equal to 2.718 in this case. And this means that our rejection region in this case is, if you watch the previous part on the z-test, you'll see that now everything is the same. It's only once you compute the critical value, the two tests are the same, the z and the t. So the rejection region in this case is t strictly bigger than the critical value, 2.718. Those are the values of t that you would reject the null hypothesis for. Okay, and so we put this in a rectangle, and the non-rejection region for this question, for this right-tailed test, is t less than or equal to the number 2.718, the critical value that we found. Okay, so because we did all of this explanation in the previous part with the z-test, I am doing this a little bit quicker than the previous one. So let's go to the next question. Now just notice that in this case you are having a left tail test. So the same thing, you only have to find the critical value here. So let's instead, you know, they have a t there. The critical value is a t, but it's better to call it CV like this. So you don't mix it up with the t that you compute from the table here when you are doing the test statistic. Okay? So that better when you compute a critical value, call it CV. Okay, so let's go back. And so this is what we need to compute. What is CV? Let's see. Now, again, to compute the critical value for a t-test, you just need to know two things. You need to know n, and from n gives you the degrees of freedom. df is always n minus 1, which is 10 minus 1 is 9. So this is the number from the table that we will look for. And the level of significance here, alpha, is 0.05. So let's go to the table now and see that because it's left tail test, it's a one tail. And the number that we have for alpha is 0.05. Okay, and the degrees of freedom, as you can see here, is 10 minus 1, which is 9. And so you just see the intersection of these two, and you get this number. So you'd say that my critical value in this case is, but look at what I'm going to do. I'm going to write, yeah, it is 1.833, but you need to put a minus sign here. This is because the t-table actually is the same for positive and negative. It's just you need to put the negative sign. So instead of this, we give you just the table that has the positive numbers, but when you have a left-tailed test, you need to remember that because it's left-tailed, look here, you can see clearly that the critical value is negative. So 0 is here, you know, this is 0, and so the critical value being here means that it's negative. So this is why we took minus 1.833. Even though if you look at the table, you will see that it's 1.833. But again, because it's a left-tailed test, you just take the negative of the number that you see in the table. So this means that this is our critical value, and again, if you go up, this is your rejection region is here, and this is the non-rejection region, the one there. And so we can write all what we found now. So here you can say, therefore, my critical value for this left-tailed t-test is equal to negative 1.833. This is a very common mistake when people take the positive value for the left-tailed test. Always remember, you take the negative value. And the best way to remember is to remember the picture that you have here. This is the picture for a left-tailed test, and it shows you that the critical value is negative. And so from this we get that my rejection region for this left-tailed t-test is going to be t less than the critical value, minus 1.833. So let's just highlight this, and we have my non-rejection region is, and let's see what it is. It's all the values of t that are bigger than or equal to the critical value, which is minus 1.833. And so this one is our non-rejection region. So if you get any t, so let's say, okay, please pay attention. If you compute this t here, the one there, and you get a number that is here or here or here or here, anywhere more than the critical value, then you will say, do not reject H0. Do not reject H0. But if the t that you compute turned out to be anywhere here, then you will reject H0. But notice here that the t-table is much nicer to use than the z-table. The z-table requires more concentration to find the numbers and so on. But for the t-table, look what happens. You only need to know that if it's left or right-tailed, then you look at the one-tail part of the table here and find your alpha. in it. And then find the degrees of freedom. Just take the sample size minus 1. Sometimes they might even give you the degrees of freedom immediately, so you just use the degrees of freedom given. But if the sample size n is given, subtract 1 from it, and then find the number under the degrees of freedom, and then look at the intersection of the alpha and the degrees of freedom. That becomes your t. But you only have to pay attention when it's left-tailed, that you take the negative of the number that you see in the table. Okay? And now I will go to the last one, which is where we have a two-tailed t-test. And now they gave us alpha 0.1 and n is 15. N is 15 immediately. You know that the degrees of freedom is 15 minus 1, which is 14. So I know that I go to the t-table and find degrees of freedom 14, and alpha equals 0.1, and it's a two-tailed test. So let's go and find the critical values in this case, because there will be two critical values. The two-tailed test is here. So you go to the table and look at the two-tail part of the table. This is the row that has the two-tail alphas. So our alpha in this case, remember it was 0.1. So it's this number here. And the degrees of freedom were 14. I have 14 degrees of freedom. So the intersection of these two is this number here, 1.761. But remember, it's a two-tail test, so you have two critical values. So in this case, you'll say that my critical value, the first one, is the negative of the one that we have here, 1.761, and the second critical value is 1.761. So let's go back and put these numbers. So I have, so I can say that this number here, the critical value 1, is negative 1.761. Let me just make sure it's 761. 761, yes. And this one here, the positive critical value, the second one, is just the negative of the other one. So it's 1.761. You see how the t-table is very easy to use. And the critical region, or the rejection region, will be two parts here. This is the first part, and this is the second part of the rejection region, where you reject the null hypothesis. And the middle is the non-rejection region. So let's write this. So you can say, therefore, I have two critical values for this t-test because it's two-tailed. My first critical value is minus 1.761. And my second critical value is the opposite number, 1.761. So this answers the question, but as you know, we add the description of our rejection region. So my rejection region in this case is, and let's look, it's either t less than minus 1.761 or t bigger than 1.761. So this is our rejection region expressed mathematically. And let's put it inside a box. And finally, last thing, and the non-rejection region in this case is, and you see here it's between the two critical values because it's a two-tail test. It's all of this here. So it is all the t that are between the two critical values, minus 1.761 and 1.761. And again, this means that if you compute the t, so I will remind you, the t is computed as x bar minus mu over, in this case sigma is unknown, so you use the sample standard deviation s over root n. So you compute this number and you check where it is. So if it, let's say, turns out to be here, this number that you found, so it's in the non-rejection region, so you say do not reject the null hypothesis H0. But if it turned out, for example, to be here or here, so if it's bigger than CV2 or less than CV1, then you will say reject the null hypothesis. So for these ones, you reject H0. For this one also here, you reject H0. And for the one here, if it turns out to be here, of course, it could be anywhere. It could be maybe here or maybe there, you know, but as long as it's between these two, then you do not reject H0. Okay, and that's it about determining critical values for z-test and for t-test. So they were the previous part was the z-test, this part is the t-test. You see the similarity between the two. The only difference is using the table. For the z-test, you use the z-table. For the t-test, you use the t-table. And for using the t-table, you need the degrees of freedom and whether the test is one tail or two tails. If it's right or left, then it's a one-tail test. If it's a two-tail, then it's, of course, a two-tail test. And so you look for the alpha in the right row. And I think I will stop here. This is more than enough. The next part now will be the part where we get our hands dirty. I mean by that is where we have a real problem that we need to compute critical values, then the test statistic, and the test statistic is computed from one of these four formulas, and then we decide whether we reject the null hypothesis or we do not reject the null hypothesis. So just watch the next part, and the four parts together would make you understand the traditional method or the critical value method very well. And after that, we will do parts on the p-value method. So up to part 4, it will make you understand the traditional method, and then I might make 1 or 2 videos to make you understand the p-value method. And I will stop here.